Rational functions, section 8.4, day 1, essential question. How do I graph and transform rational functions? Why do we learn this? Rational functions can be used to model the cost per person for group events, such as a band trip to a bowl game. A rational function is a function whose rule can be written as a ratio of two polynomials. The parent rational function is f of x equals 1 over x. Its graph is a hyperbola, which has two separate branches. Like logarithmic and exponential functions, rational functions may have asymptotes. The function f of x equals 1 over x has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So x equals 0 right here is the vertical line, y equals 0 is a horizontal line. Remember, an asymptote is a line that is approached but never touched or crossed. The rational function f of x equals 1 over x can be transformed by using methods similar to those used to transform other types of functions. All right, so here we go. F of x equals a over x minus h plus k. The a represents the vertical stretch or compression factor. If a is less than 0, then that means that there's a reflection across the x-axis. So whenever we're determining vertical stretch or compression, we're looking at the absolute value of a. A greater than 1 is a stretch, a less than 1 is a compression. The h represents the horizontal translation, left or right. Left for h less than 0, right for h greater than 0, and the k represents the vertical translation, up or down. Down means k is less than 0, up is k is greater than 0. So these translations and transformations are very similar to what we've done in prior lessons. Remember the plus or minus out on the back end? That is always reflected the up or down. Whatever is attached to the x has always reflected left or right. And it's always opposite of what you think with the left or right. And we'll go over this more in other examples, x minus h, that's going to reflect to the right. X plus h would be to the left. Example 1, using the graph of f of x equals 1 over x as a guide, describe the transformation and graph each function. So the parent function is 1 over x. So in this case, and if we use this up there, right there, or actually I'm just going to write it down here. Here we go. F of x equals a over x minus h plus k. There's no plus or minus k, so we're not going up or down, but there's something attached to the x, and it's a plus 2, which means to the left 2. So we know h is going to be, in this case, negative 2, because it's always x minus whatever h is, so x minus a minus is the plus. K is 0, so we are going to the left 2. And as you can see, the blue is the parent function, the red is a transform function, and we shifted to the left 2. And when we shift, the asymptote also will change. Let's see, example 2, yep, we are going to do example 2. Using the graph of f of x equals 1 over x as a guide, describe the transformation and graph each function. Okay, so again, in this case, there's nothing attached to the x, so h is 0, k is -3, so we're going down 3. And as you can see, again, the blue is the parent function, and the red is a transform function. Going from the blue to the red, we shifted it down 3. Example 3, we're going to save for class. And it looks like we're saving example 4 for class. The values of h and k affect the locations of the asymptotes, the domain, and the range of rational functions, whose graphs are hyperbolas. For a rational function of the form f of x equals a over x minus h plus k, the graph is a hyperbola. There is a vertical asymptote at the line x equals h, and the domain then is all x such that x cannot equal h. There is a horizontal asymptote at the line y equals k, and the range is all y such that y cannot equal k, which makes sense because remember, an asymptote is a line approached but never reached. All right, example 5. Identify the asymptotes, domain, and range of the function. Okay, I'm trying to find my pen here. Here we go. So, when I look at this, I can see that h is going to be -3 and k is going to be -2. The vertical asymptote is going to be x equals -3. Let's go back a minute. That is h. And the horizontal asymptote is your k value. So the horizontal asymptote then will be y equals -2. The domain is going to be all x such that x cannot equal -3. And the range is going to be all y such that y cannot equal -2. Pretty straightforward. If there's anything else we have to do on that one. 6, we were going to be saving for class. And now we're moving on to what a discontinuous function is and what a continuous function is. A discontinuous function is a function whose graph has one or more gaps or breaks. A continuous function is a function whose graph has no gaps or breaks. The functions you have studied before this, including linear, quadratic, polynomial, exponential, and logarithmic functions, are continuous functions. The graphs of some rational functions are not hyperbolas. So consider the rational function f of x equals x minus 3, x plus 2 divided by x plus 1, and its graph. To find the x-intercepts, we are going to look at the numerator and look to see where each of those factors are equal to 0. So we find an x-intercept. So x minus 3 equals 0. And x plus 2 equals 0. Those are the x-intercepts, 3 and -2. The asymptotes reflects where the function is not defined. And so in this case, we look to see where the denominator is equal to 0. And that's at -1. And that's where the vertical asymptote is. And as you can see from the graph, the x-intercepts are exactly where I said they would be, at -2 and 3. And again, it's in the shape of a hyperbola. And the asymptote is that vertical line that is approached but never reached. Right. So zeros and vertical asymptotes. We talked about that. If f of x equals p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1, then the function f has zeros at each real value of x, for which p of x equals 0. It's exactly what we did back here to find the x-intercepts. We set each factor in the numerator equal to 0. And vertical asymptote at each real value of x, for which q of x equals 0. Same thing we did here to find the asymptotes. It's where it's not defined, where the denominator equals 0. So we are going to identify the zeros and the vertical asymptotes of this function. So the first thing we have to do is factor. X. 4 times 1 is 4. We need to multiply to a negative 4 and add to 3. So the zeros, they are the x-intercepts. So x plus 4 equals 0, x minus 1 equals 0. There's the zeros, and the vertical asymptote is where the denominator equals 0. And as you can look at the graph, negative 4 and 1, so the graph crosses the x-axis, and the vertical asymptote is at negative 3. And notice the graph is a hyperbola. And again, neither of these graphs cross that asymptote, but they do both approach it. Example 8 is for class video questions. Identify the zeros of the function. And number 2, identify the vertical asymptote of the function.